In today's exciting episode, we are going to look at orbital motion, and we're going to start out with a little video from our friends at the Perimeter Institute up in Canada.
Hey Bob, I've been wondering if the Earth pulls on the moon like it seems to pull on this apple.
But then wouldn't the moon just fall down? How does it go around the Earth?
I don't know. If I throw the apple sideways, it still falls down. But at least it goes partway around the Earth. And if I throw it faster,
It goes farther. So?
if I throw it really fast, it goes really far around. What if I throw it so fast that it goes all the way around?
Do that again!
It's in orbit, just like the moon. It's always falling.
But never falls down.
I wonder if that was Newton's idea. He had powerful ideas.
Now, wasn't that fun? So they were talking about throwing objects so fast that they don't have time to fall down to Earth, and then they are in orbit. So this is how we launch satellites, and depending on how fast they're going, different things will happen. If it's just the right speed, you can get a nice perfect circular orbit. If you go a bit faster than that, you can get an elliptical orbit, and those can still be stable. If you go too fast, though, then it will not come back, and it will escape the gravitational field of the Earth. So for things like the International Space Station or communication satellites, we tend to not want them to fly away, but to orbit around Earth so that we can use them for something. By the way, the term satellite, we're most familiar with it in terms of things like this, communication satellites. Well, that's not a communication satellite, but anyway, man-made artificial satellites. But in astronomy, any body that's orbiting some other body is referred to as a satellite. So moons are typically referred to as satellites, and so it's just kind of a general term for an orbiting body. All right, let's look at some of the equations involved in orbital motion. Some wonderful, exciting stuff here. In the previous video, we set gravitational force, universal gravitation, equal to mg, and gave an expression for the gravitational acceleration of a planet. Now we're going to say, if I have some satellite over here, we always have solar panels on them, right? Orbiting the Earth. It's going in a nice circle here. The force acting on it is gravity, and that's the only force acting on it. It's also going in a circle, so we know there's got to be a centripetal force, so we can set the gravitational force equal to the centripetal force. And we don't want to use mg because we're significantly far off the surface of the Earth, so we want to use universal gravitation, gmm over r squared. Set that equal to mv squared over r, because that's our equation for centripetal force. Now I've got two masses here, two different types of masses. These are the two objects being attracted. In this specific case, one is the satellite and one is the Earth. This mass over here, that's the mass that's experiencing the centripetal force. So that's the mass of the satellite. So it's the satellite's mass that cancels out, as well as one of these radii here. So we get gme over r equals v squared. And it's interesting that the satellite's mass cancels out, because that means regardless of whether you've got a big giant International Space Station or a little speck of dust or anything in between, it will require the same speed to orbit at a given distance from the Earth. This distance here, r, is once again the orbital radius, so don't confuse that with the altitude or the radius of Earth. It's the entire radius of the circle. And we can use this equation for things orbiting the Sun, in which case this would be the mass of the Sun. So the mass that's left over in this equation is always the mass of the central body that's being orbited. So this turns out nicely. Oh, get ready for the animation. Oh yeah, yep, just like when you first played with PowerPoint in grade school. So there's our equation for the velocity of a body orbiting, of a satellite orbiting some other body Just depends on the mass of what it's orbiting and its distance from the center of mass of the thing it's orbiting. Now this is just as a function of distance and mass, which is nice. We might also want to know the period of a satellite just by knowing those things as well. So we've got an equation that relates velocity and period, 2 pi r over t. This is true for any object in circular motion. And then we just derived this guy, root gm over r, and we can set these guys equal to each other. So 2 pi r over t equals root gm over r. If I square both sides, I get 4 pi squared r squared over t squared equals gm over r. And I'm going to solve this guy for t, so I'll get t squared equals, that goes up there, this guy comes over here, 4 pi squared r cubed, they don't cancel, they combine to give you more r. And here's another one. You guys ready? Ta-da! Take the square root of that, pull those guys out, and there you go. The period of a satellite at a given distance from a planet of a given mass. Wonderful. Okay, let's do some examples. Actually, just one example. So if we want a geosynchronous satellite, so that means that it orbits once every 24 hours so that it stays above the same point on the Earth. These are useful for a variety of things. You can read, right? We want to, well, just read, not write. But anyway, we want to find the height above the Earth. Say I am some company and I want to put a satellite up there. I need to know where to put it so I can calculate the height needed to have that period. And so if we solve that equation we just had was t equals 2 pi root r cubed over gm. Okay, I just solved this guy for t. Now I'm going to go back and solve it for r because that's what I'm going to try to find. So if I square some things, I get back to t squared over 4 pi squared equals r cubed over gm. So r will equal the cube root of gmt squared over 4 pi squared. Wonderful, beautiful equation. Plug your numbers into this. G is still 6.67 times 10 to the negative 11th. Mass here, we want the mass of the thing being orbited, which is the mass of the Earth. You can look this up in the front cover of your book if it's not given in the problem. 5.98 times 10 to the 24th. Then we need the period. So this is a day, but we want it in seconds because the units on G are going to be seconds and whatnot. We need things to cancel out. So 24 hours times 60 minutes times 60 seconds. That whole thing gets squared. This is all under my cubed root here. And then 4 pi squared. Throw that puppy in your handy dandy calculator. And you get 4.23 times 10 to the 7th meters. Now, the question asks for the height above the Earth's surface, which is the altitude. As we've mentioned a few times, this r here is not the same as the altitude. This r is the radius of the Earth plus the altitude. So if I want to find the altitude, I need to subtract the radius of the Earth off of this, which is, let me make sure I get this right, 6.38 times 10 to the 6th meters. So subtract that, and I get 3.6 times 10 to the 7th meters is how far above the Earth's surface you would need to place this satellite in order for it to have a period of 1 day. How fast is this satellite going? Well, we have a couple of options here. We can use the equation we derived, which was root gm over r. Equivalently, you could use 2 pi r over t. Let's go ahead and use that one just because. So 2 pi r. Now, we've got to be careful of which r we're going to use. In this case, this is just the circle it's going in, so we don't want the altitude. We want the total r that we originally calculated here. So 4.23 times 10 to the 7th. And then we're going to divide that by the period, which is this guy again, 24 times 60 times 60, or 3600, not squared this time. Plug all that in, and we got to figure out how fast we need this satellite going, because if we just put it up there and don't give it the right speed, it could either fly away from Earth or come crashing back down to Earth. So we need to give it just the right amount of speed. A velocity of 3,000 meters per second, which is pretty quick. You know, maybe close to 10,000 miles per hour. But that's okay, because when you get that high, there is almost no gas up there, so there's no air resistance impeding the motion. So once you get it up to speed, it'll just kind of keep on cruising along for quite a while. Okay, last part here. Compare the speed of a satellite orbiting, compared to the speed of one orbiting at 200 kilometers. Now this here, if we convert that to kilometers, let's see, that's 3, 6, and then 7, 1, 2, 3, 4, 5, 6. So this was 3 million meters, so make that into kilometers, 3,600 kilometers. So we're going to compare it to a satellite that is quite a bit closer to Earth, and most of the satellites are quite a bit closer to Earth, but we do have some of these geosynchronous ones that are a ways out there. And we want to look at what happens to the speed. Now this is a case where we want to set up a ratio. And if I use this equation here for both satellites, I'll just call one 1 and the other one 2. So G and M are going to be the same over R1. And then I set up a ratio, V2, I guess I shouldn't have the line in the middle, but anyway, you'll get the idea, over GM. They're both orbiting Earth. G is the same for both, so we don't have to worry about those, over R2. So this stuff cancels out, and I can bring that 2 up there. I end up with a ratio, V1 to V2 equal to the square root of R2 to R1. So this is just a reflection of the fact that the velocity is proportional to the inverse square root of the distance. So to find this speed here, you could go through the same process where you could use, you could plug into here, but well, you don't know the radius there, so you could plug into this guy here and get it, but sometimes it might be easier to use this ratio here. So I'm going to call V1 the 200 kilometer satellite. I'm going to put V2 on the other side, R2 over R1, and then we just have to plug in a few numbers here. So this was V2, 3072. R2 was this distance here, so the 4.23 times 10 to the 7th. And R1 is the total orbital radius, so it's not just the 200 kilometers. We have to add the radius of the Earth to that 200 kilometers, so 6.38, and I'm going to convert it to meters because this guy up here is in meters. So times 10 to the 6 plus 200, we'll just go ahead and call it 200,000. Anyway, plug all that stuff in and you get 7,786, if we round, meters per second. So quite a bit faster at a lower altitude. Okay, a couple other things I want to look at. If you are in a space shuttle and you want to catch up with a satellite, we'll make it Sputnik this time. Just kind of look like a basketball with a few legs sticking out of it. I'm not going to be able to draw a good spaceship, but here you go. Space shuttle thingy. Yeah, that's beautiful. Okay, you're trying to catch up with this satellite. Here's Earth down here. You guys are at the same altitude. So you can't just speed up to catch up to the satellite because that will disturb your orbit. You will shoot out into an elliptical orbit or something like that, or an orbit of a higher radius. So what you need to do here, if you want to go faster, you need to drop down to a lower orbital radius, at which point you can have a stable orbit at a faster speed. Then you can catch up to the thing and then get back out to a higher orbital radius, and you can capture Sputnik, bring it back, put it in a museum or something like that. Okay, a couple other things to talk about. Weightlessness. A lot of times when we see videos of astronauts in the space station, we say that they are weightless, but technically in a Newtonian perspective they are not weightless, because weightless weight is synonymous with gravitational force, right? So we're saying that the gravitational force is 0 if they are weightless, but just like what we saw in that first video, there's still a gravitational force. That's what's causing them to go in a circle. It's just that as they fall, they also have a tangential velocity, so they don't collide with Earth. So they are in free fall, but there is still a gravitational force acting on them. So technically they're not weightless. And you can kind of see how a similar situation would occur in an elevator. If you're going up at a constant speed in an elevator, you will feel as if the elevator weren't moving, other than some vibrations and whatnot, but you don't feel heavier or lighter. If you're accelerating up, so when the elevator first starts, you feel heavier. So this should already have you thinking, well, what we perceive as weight isn't necessarily the gravitational force. What we perceive is the normal force on our feet. So if the cable breaks as you're plunging to your death, for an instant you are weightless, or you think you are, because there's no more normal force, because the shaft of the elevator, not the shaft, the frame of the elevator is falling at the same rate you are. If you were holding this box and you let go, it would just float there next to you as if you were weightless until you come hitting the bottom. So this is exactly the same situation. Whenever you are in free fall, you don't have any other forces acting on you, and so you perceive yourself as being weightless. But in a Newtonian sense, you're not. In Einstein's general relativity, he would say, yes, you are, because there's actually no experiment you could do to distinguish between this situation and actually floating in outer space. Here's your space helmet with a visor or something. So yeah, you're floating in outer space. You have some arms too. You can't distinguish between the two situations of free fall and floating in outer space. So in that paradigm, I guess you would be weightless here. But anyway, moving on. So whenever you are in free fall, even if it's for a short moment, you are weightless. And so go ahead and jump around a bit and you will experience weightlessness. In fact, that's one of the reasons why it's easier for dancers or basketball players to move their arms, because when you're in the air and you're in free fall, it's identical to being weightless, so you don't have to exert a force on your arms to overcome their weight. You do have to exert a force to get them moving if they were originally not moving, but this is one of the reasons why it tends to kind of look cooler when people are in the air and moving, is because they are in apparent weightlessness. Okay, see you next time.